Nuclear Chemistry Part 2. Understanding nuclear reactions is important, but different radionuclides vary in stability, and the different nuclides will have different rates of decay that are associated with the reaction of the nucleus in whatever decay process it is undergoing. All nuclear processes are first order, which means that they are independent of things like catalysts and temperature. The rate of a nuclear equation is equal to a constant K times its concentration. We can set up an equation to solve for the remaining reactant after any particular time from the start that is expressed as the natural log of the initial concentration divided by the current concentration set equal to the K constant times time. If we solve for the time left at 1/2 of the original concentration, we find that the time is equal to the ln of 2 over K, which is 0.693 over K. We call this half-life because it is the time that it takes for 1/2 of the material at the start to have decayed. The decay of any atom is independent from any other atoms, so the probability of any particular atom decaying is random. But overall, we can judge that from the start of the decay process, 1/2 of the material will decay within the course of a half-life. The idea of this random decay is the source of the Schrodinger's cat experiment, or thought experiment, that is described in quantum mechanical terms. Now, if we look at half-life, half-life can be used to determine the longevity of a radionuclide. We can determine how long a radioactive material will remain radioactive. The time 1/2 is, or the half-life, is the time that it takes for 1/2 of the material to react. For example, strontium-90, which was formed by atmospheric weapons testing of nuclear weapons, has a half-life of 28.8 years. So within 28.8 years, 1/2 of all the strontium-90 in the atmosphere decays. We can look at an example of a half-life like the half-life of cobalt-60, which is used in radiation therapy, that has a half-life of 5.27 years. Cobalt-60 decays by beta decay and produces gamma rays as an off-product, which are used in the radiative therapy. So looking at the calculation for the half-life with this, from this equation, I can calculate how much cobalt-60 is remaining after a certain period of time. If I, for instance, begin with 3.42 micrograms of cobalt-60, after 30 years, I can determine how much cobalt-60 remains. I start off by looking at my half-life equation and solving for the K value. 5.27 is the half-life, which is equal to the other half of the equation, 0.693 over K. Reversing that, we can have the K value equal to 0.693 over 5.27, which comes out to 0.13 or 0.131 per year. If I look at my equation for determining the remaining amount of material, I substitute 0.131 for the K value and 30 years for the T value, and set that equal to the ln of the initial concentration over the current concentration. 0.131 times 30 is 3.93, so the ln of the initial concentration over the current concentration winds up being equal to 3.93. To get rid of an ln, we have to exponentiate using e, and so exponentiating both sides with e, we wind up with e to the ln of a sub 0 over a equals e to the 3.93, which is 51. So with the ln gone, the initial concentration over the current concentration equals 51. If we plug in 3.42 micrograms for the initial concentration, then 3.42 micrograms over a equals 51. Rearranging to solve for a equals 3.42 over 51, or 0.067 micrograms. So 0.067 micrograms remain after 30 years. Nuclear fission is a different process from the transmutations that we've talked about up until this point, and it occurs with elements that have an atomic number over 80. This is either a spontaneous or a non-spontaneous process depending upon how heavy the element is. All elements that have a mass number greater than 250 undergo spontaneous nuclear fission because their nuclei are too unstable. If the atomic mass number ranges between 250 and 225, they are non-spontaneous, which means that they have to undergo some sort of process to get them started. Less than 225, generally they do not undergo fission. We can power a lot of energy from fission reactors. Fission reactors are powered by nuclear fission. For example, a nuclear fission reaction is the decay of californium-252 to barium-142 and molybdenum-106. You see that 4 neutrons are produced by this decay process, and the neutrons can go on to continue activating the decay process, bouncing around and hitting other atoms and causing them to undergo decay. The gist of a nuclear power plant is that you have the control rods and fuel rods. The fuel rods are the source of the radiative material, the fissile material. Control rods will absorb the material. A moderator surrounds the entire setup and controls the movement of the neutrons. In a light water reactor, we use regular water with enriched uranium-235, which means it's concentrated the U-235 isotope. This is what most U.S. nuclear power reactors are. A lot of the rest of the world will use what are called heavy water reactors, which use deuterium water and non-enriched uranium, which is much more expensive to come by the deuterium water, but it enables you to run the reaction without having to enrich the uranium. Either cadmium or boron are typically used as control rods, which are neutron absorbers to help to slow down the nuclear reaction. The control rods can be inserted to varying depths within the nuclear reactor and absorb differing amounts of neutrons at any particular time. The nuclear reaction heats up the moderator, which flows through a pipe and is in contact with a sample or a container of water. The water is heated by the heated moderator as it moves through the pipe and causes the water to be converted into steam. This steam is transported through tubes to a generator, just like any typical power reactor, like a coal power plant, and passing over the generator turns the generator, producing electricity. The steam is then collected in another container, which is exposed to a cooling condenser, which sucks up water from some water source like a river or a lake, runs it through the condenser, which cools off the steam, allowing it to recondense into water, and then the water is pumped back into the original reservoir to continue the process over again. There are 2 coolants in a typical nuclear reactor. One of them cools the moderator, like the moderator itself will cool the reactor and will help to keep the moderator in check. The other one will cool the steam and allow the steam to be recycled. The process of meltdown that you may be familiar with in a nuclear reactor occurs if we shut down the reactor too rapidly. It causes the reactor to overheat and will melt the fuel rods. In the 3 Mile Island disaster in the United States, we stopped the coolant too early and the emergency system failed to kick into play, which caused the reactor to overheat and melt down. Chernobyl was a bit more disastrous than 3 Mile Island because the design of the reactor was worse. It created a feedback loop which built up steam in the reactor, causing it to get hotter and hotter, and for some reason the control process fully inserted the control rods, which were made of graphite. The insertion of the control rods in the feedback loop caused an explosion which caught the graphite rods on fire and caused the roof of the reactor to catch on fire as well, which spewed a whole bunch of smoke into the surrounding area, and that smoke contained radioactive particles, which is what contaminated the whole area around Chernobyl. So meltdown is not, as some people commonly think, a nuclear explosion like a Hiroshima or Nagasaki atomic bomb, but simply a melting down of the reactor. What happened in Fukushima after the tsunami hit Japan is a similar idea of the meltdown, where the nuclear core was melting through the reactor because of the instability in the system when the power plant was affected by the earthquake. Some types of fission reactors can actually operate under what are called breeder reactors. Breeder reactors help us to combat the shortage of uranium-235 that exists in the world. A breeder reactor will typically have a composition like any other reactor that is less than a critical mass, so no nuclear reactor is able to undergo an actual nuclear explosion. But with a breeder reactor, it contains both uranium-235 or plutonium-239 and a large amount of uranium-238. Now, uranium-238 is not fissile, which means it doesn't undergo nuclear fission. However, when placed inside of a reactor, the neutrons bombarding around will strike the U-238, which will take the neutrons and absorb them into the nucleus, creating U-239. U-239 will decay to plutonium-239 or neptunium-239. Plutonium-239 can be used as a fuel source. So as the reactor is running, it actually creates additional fuel for itself over time, and that fuel can eventually repower the reactor and build new reactors. Nuclear fusion, unlike fission, is a process by which two light nuclides are combined together to make a heavier nuclide. This joins two light nuclides like hydrogen together to make helium. The energy output of a nuclear fusion process is much higher than that of a fission process. If I look at a nuclear fusion process, for instance, the combination of deuterium with tritium to make helium and a neutron, it has 1.7 times 10 to the 19 kilojoules of energy that are released per mole of hydrogen. Compare that to the combustion of methane, which releases 890 kilojoules per mole of methane. So it's a substantially large amount of energy. The nuclear fusion process occurs at extremely high temperatures, on the order of 40 million Kelvin. So far, the only way that we've been able to sustain this, because a nuclear fusion process causes the formation of plasma, all the atoms are broken down into ions in plasmatic formation, is to control it within a magnetic setup. We are currently able to control lower temperature plasma, but we have no capacity to control high temperature plasma, which would be necessary to sustain a fusion reaction. It's held within a magnetic field, which keeps it from being able to touch anything substantial, which would melt if it came in contact with the system. But the benefit of nuclear fusion is it provides limitless fuel with very little waste. The nuclides that are produced decay generally on the order of 12 to 13 years with half-life, so they decay very quickly compared to things like uranium. Now, the radionuclides are very useful for things like radiometric dating, which allows us to look at samples and determine the age of the sample based upon the amount of the radionuclide remaining in it. We can look at things from like carbon or potassium argon or uranium lead. All of these different means allow us to determine the age. The nuclide itself limits the ability that we have to date things by it. The longer the half-life of the nuclide, the older we can move back in time and date things. For instance, our carbon dating is only accurate to about 50,000 years, while potassium argon dates into billions of years. We can use radionuclides in medical settings, where it's used often for cancer treatments, as tracers to look at movement of things through the body, as a source of power for devices like pacemakers, to study metabolics, like how your body is processing things. We use it in agriculture for things like irradiation of pests or fungi, or tracking metabolism of plants to see how they're growing. We can also use radionuclides in industry to measure thickness of metal, for instance, by how much it absorbs, to monitor the flow of a system, as power sources for things like spacecraft. And it's used in research. It's used to label chemicals and see how they react. It's used to create new elements by bombarding elements together. Now, radiation is not great for us. Acute radiation exposure can cause death immediately, or it can cause long-term problems that can lead to death as well. Prolonged problems like digestive failure or immune failure, because the digestive and immune cells are the most susceptible to radiation damage, can cause people to die of malnutrition or from infection. There's an increased risk of cancer because of genetic mutation to the DNA. And there's a risk of potential genetic defects if gametes are mutated by the radiation that they're exposed to.